Thanks. I'll begin with a word of prayer. Dear Father, we thank you for this opportunity we have just to meet together and to study abstract algebra. Just bless this time we have, Lord. In your name I pray. Amen. I guess you guys have questions. Yes, no? You do?
We can ask about clarification of words in definition.
Yeah, that is allowed. Let me get my. Now, is it clarification of things the textbook has written, or is it clarification of things I have written?
No, textbook.
Okay. So where?
Problem 2. Yeah, point 4, number 9, problem 2.
All right.
So for that 2I, is it just trying to ask for like a universal way of computing cardinality?
For part D?
Part D, yeah. Part D, subsection 2.
Part D, subsection 2. Well, he's got subsections to second subsection. Subsection. So proud of myself for assigning this. Let's see here. I'm sorry. So in each case, you're supposed to find, let's see here, what's that mean?
The number of elements.
The number of elements in the quotient set, right? For the given mapping. So in other words, find the number of elements in the coset, in the quotient set of the kernel equivalents for the given map alpha. Right?
Yes.
Yeah. So alpha goes from A to N, where A is what? Count numbers from 1 to 99? Yeah, I think I usually would call that N sub 99, you know, my notation, for what it's worth. But so 1 to 99 is A, and alpha of N is equal to the sum of the digits of N. Mm-hmm. Well, it's not that many possibilities to think through. I mean, I don't know. So the question is, which numbers are equivalent under the kernel equivalence of that map, right?
Yeah.
For example, I think 1 is in a class of its own. Oh, wait a minute. No, it's not. 1 is equivalent to what? 10, yeah. But that's it, right? Yeah. Let's see here. 2 is equivalent to 20 and 11. 3 is equivalent to, yeah. Yeah. Yeah, I don't know. I would just start going through it and trying to make sure I covered everything. There might be a more clever number theory way to do it. But, I mean, the sort of abstractly, the question is so if the number has digits d1, d2, right, and another number has digits c1, c2, you're looking for d1 plus d2 equal to c1 plus c2, where d1, d2, c1, c2 are all elements of the numbers between 1 and 99. So how do you solve what's the solution set for such an equation? You know? it's one equation in, I think that was 4 unknowns. So it's going to have a lot of solutions. I'm not sure identifying it as such and looking at it from that perspective is going to be any way more efficient than just starting with the number 1 and then going to the number 2 and then going to number 3, and eventually you'll exhaust them.
Right.
And maybe on the way to doing that, you'll start to see a pattern and it'll collapse down to less work. I don't know. That's all I got to say there. I mean, I don't know some kind of secret, hidden path to Kunlun or whatever. Right. Other questions?
Can we do one from the training?
That I would like.
Problem 18 says find the Cayley table for C2 cross C4.
Ah,
Yeah.
great question. Cayley table. Now, wait a minute, is that in the mission?
No,
No, it's on the
training.
So Z2 cross Z4, is that right? Now, something I'm very annoyed I didn't cover yesterday was the direct product of groups. So, definition, if you have two groups, all right? If you have G and you have H groups, all right? And let me be more pedantic. Let's say G comma star and H comma Pac-Man groups. All right, then G cross H, the Cartesian product of G and H, has a natural group structure, which is given as follows. I can't, my writing is awful today. So what we do is we say G1, H1, G2, I'll just use juxtaposition for the multiplication in the Cartesian product. Now, it's really complicated, this is a lot to remember, but you just multiply in the way that you're given for each factor. So like G1 star G2, comma, H1 Pac-Man H2. There you go. And this is the Cartesian, this is the so-called direct product of these two groups. Okay? So like next class, I will state this and I will prove a few properties about this. Very fast. Very fast. Like the fourth Hokage. Let's see here. Sorry, too much Naruto. Now, so what I'm trying to say is that the rules for how you do Z2 cross Z4 are based on this, because you're going to add mod 2 in the first component, you're going to add mod 4 in the second component. Right? What's the size of the Cartesian product? What's the cardinality of the Cartesian product? Finite cardinality, finite set. If I have two things and I have three things, I take the Cartesian product, I have 6 total things, right? Think of the Cartesian product as a way of gluing the set you're producting with on each element of the other one. Like, if you think, here's the geometric one. If I take the circle, the circle, for example, and I Cartesian product with the reals, I would think about this as taking the real line and just sticking a circle at each point. I mean, that's to me what a Cartesian product is. It's a way of gluing this set onto that set or vice versa. So, I mean, it's a cylinder. We don't need all that here. But my point is, I don't know why I'm talking about that. I don't know. Sorry, I will do what I do. So this is 0, 0. Oops, we got to come up with an order. So getting to the point, there's 2 things in here. There's 4 things in there. Now, you're sure it was the Cayley table of the additive groups, Z2 and Z4? I'm pretty sure you're right, because Z2 star cross Z4 is not that interesting.
Right, this just.
Yeah, yeah, okay. So, so we got 0, 0, 0, 1, 0, 2, 0, 3, and then with ones. 1, 0, 1, 1, 1, 2, 1, 3. And then over here, of course, the same. Now, it's not written in stone that this is the ordering you use. The ordering that I used is what? It's called lexicographic ordering, which is sort of the mathematical analog of alphabetical, you know. I fixed the, well, anyway, it's lexicographic ordering. Let's see, I'm divided in the middle here. So let me just say, duh. And duh. Because those are obvious. So let me begin with where it's interesting. So this plus this gives me what? 0, 2. And then I'll just go down this column. How about that? Then I get what? 0, 3, 0, 0. Woohoo! 1, 1, 1, 2, 1, 3, 1, 0. Exciting, no? Exciting? Yes? Okay. Very exciting. Yes. I'll do this row. So 0, 3 plus, so that give me 0. 2 plus 3 is 1 mod 4. 0, 3 plus 0, 3 is 0, 6, which is 0, 2. That's 1, 3. Oh, wait a minute. Yeah, 1, 3. 1, 0, because 1 plus 3 is 4, which is 0 here. That gives me 1, 5, which is otherwise known as 1, 1. 0, 6, which is 0, 2. Now, as a check, you can see I did something wrong, right? You guys, tell me why I'm wrong. Look at this row I just calculated. Why am I wrong? Yeah, this is... So how about the column? Is the column okay? Are there any repeats? If there's a repeat, that means I made a miscalculation by the thing I muddled the proof of horribly last class. I should just gave up on lecturing Wednesday. I should just be like, you know what, I'm tired. Let's just go home. I should have done that. It's too late, though. So which one's wrong? One of these is wrong. The last one. Oh, because one... Oh, it's 1, 2. Okay, yeah, duh. And of course, the one that I was dying was here was 0, 3. Okay, so... Does that make sense? Let's look at a really different Cayley table. This gives me an idea. Let's take the Cartesian product. Let's this time do, let's say, Z4 cross Z4. Oh, Z4 is too big. Forget about Z4. Let's do Z2 cross Z3 star. So the way this would work is if I have A comma B times C comma D, what that's equal to is A plus C comma BD. See, and this is done, this is a mod 2 calculation, this is a mod 3 calculation, right? Now Z2 has got 0 and 1 in it. Of course, those are bars, but you'll forgive me for not writing them. Z3, I mean, you'd request that I don't write them, Z3, because then you'd have to write them, 1, 2. Those are the units in Z3. So I can look at the Cayley table for this guy and check it out. Like, this is like a pretty decent I mean, it's actually a pretty nice test question because it's pretty simple, and I can easily see if you guys actually understand the concept of multiplicative versus additive, and what's a Cayley table, what's the direct product of groups. I mean, there's so much goodness here, and it's also, frankly, an easy problem. So there's just 4 things here, right? So the Cayley table is a little bit more manageable. How many entries were in the other one if I finished it? Yeah, 64. Good grief. By the way, so beware of misinterpreting a multiplicative problem as an additive problem, right? If I ask you a question about like multiplicative Z8, how many things are in Z8 star? 4 things, 1, 3, 5, 7. But if I ask you about Z additive, it's got 0, 1, 2, 3, 4, 5, 6, 7 under addition, right? So the question, if you misinterpret the question, it can make it much worse. Anyway, so here, we gotta be careful. We're doing addition in the first component, we're doing multiplication in the second component. Mod 2 and mod 3. Oh, this is gonna mess my head up. Let's see here. So I got 0, 0. I'm adding 0, 1. I decided, I made a command and control decision here, which is that my brain is set up so that I should do the calculation this way for sure. See what I'm doing? I am, what's the saying? Be where you are, do what you're doing. Let's see here. So, I mean, I'm going to stay in the mod 2 world, additive mod 2 world for this first part of this calculation. And then I will shift to multiplication to get the second component here. But goodness gracious, not to start with. I think this will be more likely for me to make less mistakes. I mean, you can do it however you like, but 1 times 1, 1. 1 times 2, 2. Why am I thinking through this? What has to happen in the first what has to happen in the first column and row if we did things right? Right. These, right? The place which is always interesting right, this is the part that's really interesting, right? Most interesting. What happens down in here? 2 times 2 is 4. Mod 3 is 1, right? Then 1 times 2 is 2. 2 times 2 is 4, which is 1, yeah. Can't do math. Answer here. 2. 1 times 1 is 1. 1 times 2 is 2. Let's see here. 2 times 2 is 4. 4 is 1. 2 times 1 is 2. 2 times 2 is 4, which is 1 mod 3. What's E in this group? If I call this thing G, what is the identity in this group? What's that? 0, 1. Very good. So what would like 1, 2 inverse would be equal to what? Let's check it. 1, 2, 1, 2 equal to 1 plus 1, 2 times 2, right? And I think we have a winner. That's 0, 1. Hooray! Yeah. And this is commutative, right? So it's going to be an inverse the other way as well. This wasn't a problem on the mission, was it? I should have made this a problem on the mission. Oh, well, it's too late. Do you guys have other questions? Before I mean, I can start making up other flavor choices for this example set, but I think it's that's probably good. Good place to just kind of stop there for the moment.
Can you talk about section 1.4, number 22?
Now, is that in the mission or? It's in the training. Oh, then I can do it. So we're supposed to show that oh, I was about to say, I read that when I first read it. I read it AN intersect SN is equal to AN again. I'm like, well, yeah, if you take the universe and you intersect with the set, of course you get the set back again. But I just noticed there's an n plus 1, isn't there? So let's try this again. Oh, I should show you guys before I forget. You know, I have links to sites that do the math for you, right? And before I forget, I should show you. I found this one. Where does that thing go? I know you guys can't see it yet. It's Subgroup Lattice and Cayley Table Generator by John Jones. It's number 10 in my list of links to math, list of websites. Do the math for you on my webpage, you know. If you can't find it, email me, I'll help you. Of course, if you're looking at what I'm doing right now, you can probably Google it and find it, but I don't mind answering your email about that. Come on. Come on. Thank you. So, check this out. If we want to look at, let's say, what did we just do? 2 comma 4, right? Cool, huh?
We just print that out and stick it on.
I'd like for you to think through it. But now this is not especially like, yeah, okay, whatever. But the cool thing is, and we'll talk about this some hopefully next time, but it also will create subgroup diagrams. And now, I don't entirely understand his diagrams, I'll admit. But when I look at them, it means things. I mean, it means something. I think it actually, I mean, I'm joking. If I spent more time to understand his nomenclature, I could figure out what he's saying with this. But, I mean, it's a standard thing he's doing. It's just his labels I don't quite get yet. It's just me. And I have found a bug in one of his diagrams. I mean, possible subgroup diagram, let's say, okay? But you can check it against the one the books give and see if it's right on those. It is right usually. I just found a sufficiently awful thing that I think it was wrong on. I probably should have emailed him about it. I'm a bad person. Let's see here. Where was I? But it does other ones too, right? You can look at the Cayley table for like DN, which I was going to talk about last time. That's the dihedral group. Oh, fine. D4, whatever. What? Oh, I haven't looked at this before. Interesting. So the D4 is the group. It's the dihedral group. What, you know what dihedral means? What is you know what hedra means? Like what's polyhedra? Poly is many, hedra faces. So dihedral means two faces. So if you want to like call somebody, like you're so dihedral, just say it to them. They'll never know what you're talking about. I will work that into a joke about something later. You guys will get it. No one else will. So that's good. That's what I'm looking for. Now the dihedral group is the group of symmetries on a square which can be turned over. So like you can rotate by 90 degrees, 180 degrees, 270 degrees. Those are the rotations. R, E, R squared, R cubed. Those are rotations by either 90, 180, 270, 360. And these are reflections, either across that diagonal, across the vertical, across the other diagonal, or across the horizontal. I like his notation. It's kind of cute. But we'll talk about that next time, probably. I mean, well, who knows what I'll actually talk about. I'll get wrapped up in some kind of discussion about 0 or 1. It'll be fascinating. Then anyway, I'll shut up. What else has it got? Mystery. Whoa. 66? What? What? This is, I mean, what is this? Oh, I think you're supposed to, I think the game here is to identify which group it is. Maybe.
That doesn't seem like much of a game.
I'm sorry. I should put this away. I see I could easily spend an hour on it, and it wouldn't help you guys that much. But anyway, that's there. That I think at times would be a very useful resource for you, especially as you come across certain examples. Do you want to check your work or something? Okay. It's especially helpful when you're trying to think about possible subgroups, because whatever subgroup is, I know, but at some point we'll learn what those are. Fine. All right, so what was it? It was what was the count? We were trying to show an plus 1, was it? Oh, an is equal to or subset of? Oh, equal to. And it was n plus, intersect what? Sn or Sn plus 1? Oh.
For n greater than equal to 3.
And number 13 training, number, you said 20, 1.4, number 22? Yeah. All right. So do anybody here have an idea? I mean, what is AN to start with, right? I mean, that would, to understand the question, we should understand what AN is. So AN is equal to sigma in Sn, right? Well, let's just say permutations. With what? The sign SIGN of sigma equal to 1. Now this is just a fancy way of saying sigma is product of how many? Of even number of transpositions. So it can be proved. You can show that no matter how you decompose a given permutation into transpositions, the number of transpositions making up that decomposition will be either even or odd, no matter how you reformat the cycle. So like, let me, here, for example, we had sigma equal to 1, 2, 3. All right. How can you rewrite that as a product of transpositions? What was the trick? How'd it go? Was it 1, 3, 1, 2? Is that it? I can't remember. Did that work? 1 goes to 2. Okay. 2 goes to 1, goes to 3. 3, let's see here, 3 goes nowhere. 3 goes back to 1. Yeah, I think those are equal. Is that right? Now, this is also equal to, check this out, 1, 3, 1, 2, 2, 3, 2, 3. I mean, just to be dumb. That's the identity permutation, right? But you notice the thing is, no matter how many, I mean, and you can go through this for, the proof is in Nicholson. It's just not especially interesting. I don't know, maybe it's interesting, whatever. But the number of transpositions, if it's even before, it's going to still be even, no matter how you like rewrite it. So long story short, a odd length cycle ends up being an even permutation. An even length cycle ends up being an odd permutation, right? And so how about if you have, what if you have two even permutations? If sigma and alpha are both even, what happens? What's that again? I mean, yeah, right, because you've got an even number of transpositions composed with even number, still have an even number of even number of, so I mean, the formula basically is this: the sign of the composition is equal to the sign of sigma plus the sign of alpha mod 2. Is sine, well, I'm sorry. Did he define sine to be 0 and 1, or did he define it to be plus and minus 1? Ah, curses. He did plus or minus 1? So this is product. There we go. Sometimes I might talk about the parity of a permutation being 0 or 1. 0 being the even ones, 1 being the odd one. But we can think about it minus 1 and 1. Minus 1 being odd, 1 being even. So like minus 1 times minus 1 is 1, right? The product of odd permutations is even, because if you have an odd number and then you tack on another odd number, put them together, you got an even number, right? Okay, anyway, that's what AN is. It's permutations which can be written as a product of an even number of transpositions, right? Okay, so what is AN? This would be equal to sigma in Sn, right? Such that what? Such that, sigma is product of even number of transpositions. I wish I could, well, anyway, there it is. How about AN plus 1? This is sigma in Sn plus 1, right? Such that sigma is product of even number of transpositions, right? A transposition, again, is a cycle of length 2. So it might be helpful to look at this for a low dimensional case to get an idea for the argument we need here. Let's see here. Let's try this out. And this is probably a good exercise anyway, because we haven't actually looked at a sub n for small n yet, have we? Not really. So how about a sub 3? I mean, S3, what's it have in it? Of course, we got the identity, right? You got 1, 2. You got 1, 3, 2, 3, 1, 2, 3, right? And what else? 2, 1, 3, 2, 1, 3. Also known as 1, 3, 2. I think that's it, right? Oh no. I just sneezed into the mic. Joke's on them. teach you to listen with headphones, but your left ear is really hurting now. Sorry. I don't know why. I thought this was a stereo mic, but it's recording just the left ear again. I don't know what's the deal. I mean, I don't know. I guess I spend $600 and get a proper mic, but somehow I don't. I'm not allowed. Let's see here. And I'm glad my wife doesn't let me spend that money also, because it would be stupid. Okay, so these are even, right? So odd. This guy's got 0 transposition, so it's, I mean, you could if you want, you could say, oh, this is 1, 2, 1, 2. You can see it's even if you don't believe 0 is even, but 0 is even, so whatever. Now these are both even because you can rewrite them. What did we just say? I just already. Oh, 1, 2, 1, 3. Is that right? Oh, okay. Why don't I believe it?
It might have been 1, 3, 1.
I don't think it is.
I think it's 1, 3, 1, 2, isn't it? I should remember this stupid trick. 1 goes to 2. 2 goes nowhere. And 2 goes to 1, but 1 goes to 3, so 2 goes to 3. 3 goes nowhere. 3 goes to 5. Oh, yeah. Anyway, there's like a couple different strategies for doing this. That's one of them. You go to the last shall be first, and then you work your way back. So if I had 1, 2, 3, 4, 5, the trick is 1, 5, 1, 4, 1, 3, 1, 2, like that. Just remember the first stays first, and then the last shall be first, and hope that doesn't get twisted around in your mind. Just check it, whatever. Guess something and check it. Maybe you remember the pattern right. Anyway. Okay, I'm sorry. So what's A3? I'm going to say 1, 3, 2. All right. What's A4? No, it's got A4 has A3 in it already, right? I mean, because we interpret these as being permutations on 4 things by default, right? What's new? We have some new 3 cycles, right? Those are even permutations. What are the new 3 cycles in A4? Yeah, 1, 2, 4. 1, 4, 2. Yeah, 1, 3, 4. 1, 4, 3? Ah, 2, 3, 4. Oh. 2, 4, 3. Does this ever end? Hi. Does that make sense? I'm not sure I believe you guys. The order of A4, right, is 1/2 the order of S4. The order of S4 is 4 factorial. So A4 should always have like 4 factorial divided by 2 things in it, which is what? 12 things, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. Ah, we're missing something.
There's no way 4 cycles can be written as even.
Yeah, 4 cycles are
Always up.
or odd, yeah.
3, 1, 2.
3,
Oh, yeah, we didn't do any of the ones that start with 3.
that must be it. So we got 3 what? 3, 3, 1,
3, 1, 2 is 1, 2, 3.
oh, but 3, 1, 4.
Or 3, 4.
Do we have 3, 1? We got 3, 3, 1. This is equal to 3, 1, 4, right?
Yes, even if they start with 3. Doesn't matter what it starts with, it matters what it doesn't have. So we got all the ones that matter.
Oh no! We broke the alternating group. This is not good. AN is the alternating group. SN is the symmetric group. Don't ask me why these names are given. I do not know.
So you get 2 without 4, 2 without 3, 2 without 2, and 2 without 1.
And we need how many more?
Yeah, maybe it even helps us to look at them in terms of transpositions. Maybe not. I don't know. Let's try. So we got. What are the transpositions in A4 to work with? We got what? You've got 1, 1, 2, 1, 3, 1, 4, right? 2, 3, 2, 4, and 3, 4, right? Them's your transpositions in S4, right? Anything else? I don't think so. That's it, right? That's all the possible ways to take two distinct elements from numbers 1 through 4. Am I right? Okay.
Well, isn't that even?
One transposition by its lonesome is an odd permutation by definition.
He's not actually generating something, he's just listing them.
Oh, I'm listing them. So my point is we can put them together different ways to make a. So we can either do 1, 2, 1, 2, 1, 3, right? We can do 1, 2, 1, 4. We can do 1, 2, 2, 3. We can do 1, 2, 2, 4. We can do 1, 2, 3, 4. Did I get everything? 1, 3, 1, 4, 2, 3, 2, 4, 3, 4. What else do we have? We have 1, 3, right? 1, 3, 1, 4. 1, 3, 2, 3. 1, 3, 2, 4. 1, 3, 3, 4, yeah? What's that?
1, 3, 1, 2 is not different than 1, 2.
1, 3.
1, 2,
Well, let's just keep going here. What's next? 1, 4, right? 2, 3. 1, 4, 2, 4. 1, 4, 3, 4. What's next? 2, 3? Yeah. 2, 4, okay. 2, 3, 3, 4. And finally, 2, 4, 3, 4. How many are there? I mean, these are even by construction, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Oh no! We want 12, right? I mean, there's also the E, yeah? Are they unique is a good question. This is actually a great calculation. Let's work them out. What's this equal to? If I start with 1, what do I get? 1, 3. 3 goes to 2. Guess that's it, huh? And this one? then this one? I hope 3 goes to 1, yeah. And then this one? 1, 2, 4. Okay. Starting to notice a pattern here. I mean, we could simplify some of these using this, couldn't we? Oh, maybe that's just the one. Curses. I mean, I'm guessing this is 2, 4 if I had noticed my pattern right. These being 3? Yeah. Uh-oh.
1, 2, 3, 4. That is 4. That would be a 4 transposition. Or that would be
It would be just 2.
1, 2, 3, 4. That would have 1.
It's a product of 2 transpositions, so it's even. And this is not 1, 2, 3, 4. This is 1 goes to 2, right?
Oh, okay. We just,
I mean, this is, it is what it is.
so that was what
Yeah.
we're missing.
It is what it is, right? So that one is what it is. Can any of these be simplified? 1 goes to 4, right? 4 goes to 1, 3, right? 1 goes to 3, 3 goes to, that's right, 1 goes to 3, 3 goes to 2, yeah? You guys correct me if I'm wrong, I'm trying to do these fast. 1 goes to 3, 3 goes to,
So I think
S-
what
say-
we're missing are the ones that have 1, 2, 3, and 4.
oh, okay, so with ones,
So those
right,
1,
okay.
2, 3, 4, and 1, 3, 2, 4.
So, 1, what's that one? What? 1, 1, 3, 4, okay. This one?
That stays.
This stays? Oh, okay. Yeah, I'm sorry. You guys pick up on the pattern.
1,
Good.
4,
1, 4, 2. Any of these overlapped yet?
2. Yeah, that one did.
Aha. And then this one?
1, 4, 3.
And this one?
2, 3, 4.
This one?
No, I think that one's 2, 4, 3.
Oh, sorry.
2, 4,
Yeah,
3.
my bad.
And this one?
This is 2, 3, 4.
2, 3, 4. This one?
2, 4, 3.
That one overlapped.
Yeah.
So we have 3 that overlap. We're good.
So how many we got? 1, 2, 3, 4, 5, 6, 7, 8.
Oh, wait, no, that one overlapped.
Oh.
1, 3, 2.
Oh, tell you what, let me cross out the ones that overlap. Let me cross the second occurrence out with a red. That one doesn't count, right? Do we already have 1, 4, 2? We already had this one. Yeah. Already had this one. Okay. 2, 4, 3. Oh, this one doesn't count then. So how many we got? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And what's missing? E. All right. Any patterns? What's new in A4? I guess is the question, right? How do A4 and A3 relate?
A3 is a subset of A4.
Yeah, A3 is a subset A4, true. Let's hear. How many new three cycles do we have? Yeah, we got 1, 2, 3, 4. Yeah, 5, 6. 6 new 3 cycles. And we've got 3 new 2 cycles, right? Wait a minute, 3? No, 1. Yeah, 3. The ones with 4 in it, right? Any ideas? I mean, I'm not much worried if we find the answer right now. I think this is useful experience that we're getting here, looking at these. There is a simple proof of this. Like, there's a way, but I don't remember it off the top of my head. Something sneaky to establish this equality. I don't remember it right at the moment, though.
Is there a way to show that A sub n is a subset of A sub n plus 1?
I think that's true by definition of the alternating group. I mean, so
So can we assume that for our group, since we know?
okay, so well, exactly. I mean, that much is true. You're right. A sub n is a subset of a n plus 1. According to our convention of viewing n plus 1 permutations as n permutations, and you're absolutely right. A n is a subset of Sn. So the one, I mean, that's a useful comment, I think, Sabrina's making, which is that it's clear that A sub n is a subset of the intersection of a n plus 1 with Sn, right? The real question, right, is why is Sn intersect a n plus 1 or vice versa a subset of a n, right? That's the thing that we have left to show. If we can show both, then we have equality, right? But maybe that's also easy. I don't know. What does it mean to be in the intersection here? Oh, I'm an idiot. Look at that. Duh. If something's in a n plus 1, it's an even permutation, right? If something's in Sn, what's it mean? It's a permutation on... It means... Here's the way we can look at Sn as it... I mean, how would you describe something that's in Sn as a subset of Sn plus 1? What would you say about sigma in here? What can we say about sigma of n plus 1? When we say like 1, 2, 3 is a permutation on 4 things, what's our understanding? Is that 4 is what? It's fixed, right? So my point to you is that if sigma is in Sn, which is viewed as a subset of Sn plus 1, we're assuming that sigma of n plus 1 is n plus 1 again. Right? So when I think about this, I don't know. I mean, so if I pick a permutation in the intersection of these two things, from the fact that it's an a n plus 1, I have that it's the product of an even number of transpositions. Right? From the fact that it's an Sn, I have that it fixes n plus 1, and so it can be viewed as a permutation in Sn. So it's a permutation in Sn with an even number of transpositions, which means what? It's in there.
When you say it fixes n plus 1, you mean like it takes away the problem?
I mean it sends n plus 1 to n plus 1. In here, these send 4 to 4, for example. I feel like it seems very trivial to me. I wonder if I'm like glossing over something. Yeah. I will ponder these things. If I have more, I'll tell you later. So I think I'm out of time, right? If you guys have any other pressing questions, I can take it though. If you have one. No, nothing. Okay. Thanks, guys. Thanks for finishing Chris's taping. Very helpful.